So two electric charges can exert forces on each other. In fact, as you saw, the charges don't even have to be touching each other. As soon as they're close, there's a force that's going to be there. So we can think about that action at a distance force like a force field. You're quite familiar with this. You know you don't have to be touching the Earth to feel the gravitational pull of the Earth. There's a gravitational field that surrounds it, and that's what generates the idea of the force. Now, in the case of charges, we'd like to describe what that electric field looks like. Now, one way to do that is to think about having a single charge and putting a test charge at various locations and seeing what size force is exerted on that test charge. So here we have a positive charge. Let's imagine putting some test charge nearby. But what size or what sign of charge should we use? By convention, again thanks to Benjamin Franklin, we'll put a positive charge somewhere nearby, for example over here. Let's make it a positive charge, and that's going to be our test charge. What kind of force would that charge experience from our positive charge in the middle? Well, it will experience a repulsive force because it's the same size charge. It'll be a force off in that direction. And of course we could use Coulomb's law to calculate it. So we could have a field that had a force in that direction. What about a test charge over here? What if we moved our test charge to be placed over here? Again, it's a positive test charge, so we could imagine here we would have a force that pointed out in that direction. And we could draw a whole bunch of lines all around this central positive charge that would represent the field of forces that a test charge would feel. In fact, what we'll do is just draw some of those lines, and where the lines are really closely spaced, that's a strong force, and where the lines are separated by much larger distances, that's a weak force, and the arrow on the line will indicate. Now we're going to decide that we call our electric field, instead of being just the force, because we don't really care about that test charge. We can put a big charge there or a small charge there. We want to know the field from our central charge here. So we'll say that our electric field is the force divided by the test charge. It's the force per unit charge. And if you go back and think about that, the force was K, Q, Q test. There are our two charges, divided by R squared. And we're going to divide all of that through by our test charge. And so what we end up with when that charge cancels that charge is simply an electric field that only depends upon our charge in the middle and gets smaller like R squared. Here are the lines drawn around a positive charge in the middle. You can see they're radiating uniformly out, and in fact it's a positive charge in the middle. Let's put a plus next to there to remind us. And so these lines will all move outwards. And you can see that they're much closely spaced towards the middle where the charge is located, and they get further and further apart as we move away from the charge. That tells us the electric field is stronger close to the charge and gets smaller the further away that we go. If we have more than one charge, we have to think about the force that would be on a test charge from all of the charges and add them up, of course, like vectors, because that's how forces add. So let's do an example here where we put another positive charge near our first positive charge. And these are the field lines. Again, because they're positive charges, a positive test charge would be moving away. So all of these lines here have arrows that move away from the test charge. So the general rule here is that electric fields for positive charges move away from the positive charge. Now, of course, if there was a charge in this region in here somewhere, it would feel repelled by this and also feel repelled by this. And so the field here is actually quite weak. Those two forces are cancelling out. If we had a charge in this region over here, it's going to feel repelled by both of those charges essentially in a similar direction. And so the lines get closely spaced and the field becomes quite large in this region over here. What if we change one of those charges to a negative charge? That blue charge there is indicating a negative charge. Well, if we put a positive test charge near a negative charge, then it will feel a force towards that negative charge. And so field lines arrive on negative charges. That's the direction that a positive charge would move. And of course they still leave positive charges. And you can see these lines here go from positive charges over to negative charges. Again, if we had a positive test charge in the middle here somewhere, it would be repelled by the positive charge and attracted by the negative charge. And so the field is quite strong in that region. The repulsion from the positive and the attraction to the negative are pointing in the same direction. Somewhere further away, over here for example, Here we're not feeling much effect at all from the negative charge because remember that force drops off like 1 over the square of the distance. So the field out here looks very much like the field you would see anyway from a positive charge. And similarly over here, the field looks very much like you would see anyway from a negative charge. So these electric fields say to us that the charges nearby will feel a force, and of course those charges will most likely move in response to that force. They will accelerate, like we learnt in our motion module. A nice way to think about it, just like we did in the motion module, was that force acting upon a charge that's being accelerated will give rise to work being done. So we can think about this in terms of work and energy. In fact, we can think about the work done as a charge moves through a field. Now, as you saw, those electric fields around those point charges were kind of complicated in that the field got weaker and weaker the further you went away. It dropped off again like 1 over r squared. We're going to use a simpler system now where our electric field is much, much more uniform, a bit like a uniform gravitational field. You can see here we have 2 plates. Perhaps they're metal plates that have been charged up by being rubbed by something, or maybe they've been connected to a battery, as we'll see later. But one of those plates, the upper one, has a negative charge on it, and the lower one has a positive charge on it. And if you now think about the direction that a test charge would move, you can soon see that the field lines here will go from the positive plate up to the negative plate. That's the direction of the force, and we'll try to draw them nice and uniformly spaced here because in fact in the region between the plates, the field, the electric field here, is actually quite uniform. As we get towards the edges of the plates, things aren't quite so symmetric, and we'll try to avoid that area, but in fact the field will start to bulge out a little bit as I've drawn just there. It still points from the positive towards the negative, but it's not quite as uniform. So there's our electric field. In this case it points from down to up across our page. Now, if we had it, and let's say these plates here are a distance d apart. If a charge, a positive charge, was to sit in here somewhere, it will feel a force upwards from the electric field, and if it was to move from one plate to the other, then the work done on that would equal the force multiplied by the distance, as we've seen before. Or if you like, we can call that the electric charge on this, let's call this charge here Q, times the electric field times the distance. Now once again, often we want to describe the field here, not just the charge that's in there. So we're going to talk about the work done per unit charge. And that will just equal the electric field multiplied by the distance we've moved through. And we actually call that, rather than electric potential energy, we just call that electric potential. And that's a term we'll be using a reasonable amount. It's potential energy per unit charge. It's measured in units of volts, and so quite often we'll call that the voltage. Now one thing to note here is that I drew a positive charge moving in the direction that the electric field points. It turns out that although Benjamin Franklin got quite a few things right, one of the things he didn't get right was to decide that positive charges were the things we would think about. It turns out that most charges that move are actually negative charges. Mostly they're electrons, and electrons have a negative charge. So in fact, if we put a negative charge in this field, the negative charge will feel a force in the opposite direction to the field. It will feel a force pushing it downwards. And we'll find out in our next topic when we start to discuss how charges move and form electric current, that in fact it's the negative charges that move, but we still have to describe everything as if it was the flow of positive charge.